who's done data analysis here before on any level? One, two. Well, you have, definitely. But rest of you have. So there's people not putting their hands up who definitely have, I know. But anyway, so I'm going to start from the very basics, because I'm assuming that your level of understanding may not be great. And, you know, I think despite this being a course about biolayout, there's a need to go through some other things. I mean, I don't want to spend too long on this. I want you to get on hands-on as soon as possible, but I think it would be remiss of me to talk about how to use biolayout without actually mentioning some of the things that can happen to data before you get to biolayout. So it's sort of very, very quick introduction to graph-based analysis, and then obviously we're into biolayout. So as I guess we've all know, over the last decade or so, we have gone from doing one gene at once to doing everything, or measuring one thing at once and to measuring everything. And whilst this kind of, I suppose, represents the most abundant form of biological data we have, transcriptomics data, been around the longest, actually was the cause for us to develop biolayout, but actually, to the end of the day, it could be any type of platform you're looking at, really, because you take a bit of biology, you chuck it in there, and what you get is this big matrix of numbers, and you go, ah, I never suspected that, even though you knew it was coming. So what is a challenge, certainly, is how we deal with this data. And certainly, you know, there's lots of reasons why we might want to do a gene expression study. Certainly, if you know where a gene's expressed, you might know something about what it does. So a gene only expressed in the eye is probably got something to do with vision. Some genes are not so informative by their expression. They're expressed everywhere, and so it doesn't really tell you what it might do. But of course, we all, as Claire is one of the people, want to look at what happens when we tweak a biological system or there's a change in a biological system. So it may be during development, biological processes, it may be circadian rhythms. We may do a knockout of a mouse and then go, well, it still looks fine. Why? And so we go to transcriptomics to see if there's any underlying change in their expression pattern. Of course, there's disease or pathogenicity. What happens when we poke macrophages with LPS and things like that. So there's lots of reasons why we might want to do this stuff, and you'll all have your own reasons and why you've decided to do an array and experiment, and we can talk about those. Now, I think the thing to say is that there is tons of this data around. So this was, taken in 2014, a snapshot of the two main expression databases, GEO, Gene Expression Omnibus, from the US or the NIH version of the data repository, and Array Express, or European equivalent. But you can see, you know, 1.5 million arrays worth of data already in the public domain, and that's out of date already. One of the things you must consider before you just embark on an array experiment is what data's there already. So if Claire had looked, she'd find there's lots of LPS experiments out there.
Not on rats.
Not on rats, is that right?
Yeah.
Okay, so you did check. But, you know, it's quite often that you do find that someone has thought of a very similar experiment to you, and they've already done it, and it's worth going to have a look at that. Because essentially, if you can't analyse their very similar data, you're not going to be able to analyse your own. And if you don't understand what some of the issues are with the data, then... So anyway, lots of data, and one of the nice things about what I'm about to teach today is you can go there, you can grab it, you can look at it, and within 20 minutes, half an hour, once you're trained in the art, you'll be able to actually understand what this data looks like and be able to get an opinion on that data very quickly, which is an extremely useful part to be able to do. So the problem is, of course, is that big data, big challenges. So it used to be just called data. Now the world is calling it big data, because it's not just biology that has it. Every sort of industrial sector is collecting data from your mobile phones, from your internet connections, your social network is all streaming in, and it's now called big data. It's noisy, it's possibly flawed, and we're going to just talk a little bit about that before we go on, because actually one of the things that you often find when looking at data actually is you find that it's flawed and it isn't quite what you thought it might be. I suppose the reason that we ended up developing biolayout was that basically other approaches are very slow. Nobody does the same analysis the same way, and it's not great. And actually, most of the approaches are quite limiting in terms of what you can begin to gain from a given data set, and we wanted a better way of doing it. And this is down to complex and often very statistical pipelines where I read papers sometimes, I have no idea what they did. You read it and you read what they did, and then you look at the answer and go, I don't know quite what they did here, and I don't therefore believe with their answer. That quite often what you will get given back is a ranked gene list. So you do a statistical analysis, and of course the obvious thing that you want to do is give your list back and you rank it according to p-value or fold change. That kind of is a false way of looking at data, because it assumes that the thing which is the biggest change and the biggest significance is the most interesting, which is not the case. And of course what we'll come on to is poor and static visualizations. With all of this in hand, I often read papers and I don't actually believe the answer that they give in that paper, because actually they don't really understand the data themselves. And one thing about biolayout is that it does work very well. So I guess all of you are familiar with those type of images. We won't be generating any of them today, which may or may not be a good thing. I'm not going to bore you with all the ways you could analyze data. I'm just going to tell you about one way you can analyze data, and I would argue the best way of looking at data. I guess the other thing to say is that there's tools out there, lots of tools out there. I suppose if you're a proper bioinformatician, you'll be using Bioconductor and R as a tool to drive your analysis. You may have bought Partec and be doing Partec and what that can do. You may be using Ingenuity as a means to explain the results. But we can talk about those if you want to, but I'm not really going to go into that. The problem I find with all of this is it's very driven by your question. Okay, you have to go in there and you ask questions, and then you get things like heat maps, which I absolutely abhor, because I just don't think they actually show what the data looks like underneath. When you turn something into a heat map, all the numbers become screwed up because you've had to actually make things red and green and twist around with your data. But and a lot of the things that I really get annoyed about is a lot of people do analysis and they never look at the data. They look at their gene lists. Their gene lists are everything, but they never actually go back and actually look at the raw values that led to that gene list. Anyway, I should stop ranting.